So if we look at our work energy theorem with the potential energy in there, what we've done is we've moved the work by forces that make potential energies. So like gravity and springs, for example, and put them in the potential energy term, and then we've left them off of this side. And so this is just work done by forces, by other forces, like me pushing with a rope, me pulling with a rope, or me pushing, or friction, or something like that. This is the forces that that I can store energy in, and this is the kinetic energy. And so I'll be a little more specific about this later on. We get the change in potential energy plus the change in kinetic energy is equal to 0, because there's no work done by these guys. And so when I pick this up like this, and if I start from this position, right, the marker, and just drop it, then once it's released, it's just gravity and kinetic energy that are involved. No other forces are doing work, at least until it hits the table. And so I can write my formula this way, and I can say, look, PE final minus PE initial, and I'll be less specific that it's gravity in this case, plus KE final minus kinetic energy initial is 0. I can move the initials to one side, and I get PE final plus KE final equals PE initial plus KE initial. In other words, so I took the two with the negative sign, moved them to the other side, they're positive. In other words, the total potential energy plus kinetic is equal to the, initially, is equal to the final. And so, like when we were dropping the box earlier, when the box is first released, it's got no kinetic energy, and all of its energy is potential energy, right? Here I can say kinetic energy initial equals 0, potential energy initial equals mgh, right? And then right before it hits the ground, now potential energy final is equal to 0, and kinetic energy final is equal to 1/2. Let me write it back a little bit. KE final is equal to 1/2 mv squared. Hopefully that's on the screen. And so I go from having all potential and no kinetic to all kinetic and no potential. And so this is sort of a statement of conservation of energy. And really what it's saying is conservation of, I would say, mechanical energy. But this is a statement of conservation of energy. The initial plus final, the final kinetic plus potential equals the initial kinetic plus potential, because no other work is being done. In this case, when no other work is being done, I get a conservation of energy. And this is often used as the first law of thermodynamics. We'll do some more examples. A 200 kilogram loaded roller coaster car is traveling at 15 meters per second on a frictionless horizontal track. When it drops 30 meters, what is its speed at the bottom? And so this is an energy problem. Notice this would be a hard problem to solve using Newton's laws of forces, like we were doing in the last few chapters, because the ramp isn't straight, and so the forces that are pushing it down the track are constantly varying. This would be a very hard problem to solve that way, but using conservation of energy, it's pretty easy. We don't have any friction acting, and so the only force we have acting is gravity, except there's also the normal force. And gravity is doing work, but notice the normal force isn't, because no matter where the car is on this track, whether it's at the top or here, the normal force is always perpendicular. There's the normal force, right? Here's the normal force. Here's the normal force. the normal force is perpendicular to the motion. So the work done by the normal force is 0. And so there are really no other forces besides gravity that are actually doing work on the car. And so that means that I can use conservation of energy. I can say, look, the change in potential energy plus the change in kinetic energy is 0. And that means we already shown that means PE final plus KE final. Oh, I'll just write it out. So change in potential energy is PE final minus PE initial plus change in kinetic energy, which is KE final minus KE initial, is equal to 0 because there's no external work, no other work's done. This is our work energy equation, but the work is 0, right? And so I move the finals to one side and the initials to the other, and I say PE final plus KE final equals PE initial plus KE initial, right? And if you remember the definition of the potential energy, at least for gravity, which is what I'm kind of assuming on these guys, is mass times gravity times height. And so we have to pick heights. And I'll show you in a minute that it doesn't matter as long as we're consistent. And so I'm going to pick, H final equals 0 here because it's the lowest point, and that way I won't have to deal with negative numbers. And I'll put H initial equals to 30 meters over there, if you can see that. Anyway, that's my initial height. And so this equation becomes mgh, I'll write it over here since I don't have a lot of room, mgh plus 1/2 mv squared is equal to mgh naught, and now I'll have to get rid of that, plus 1/2 mv naught squared. Right. And so the thing I'm looking for is this v, because that's my v at the bottom. I have v naught at the top. V equals question mark right there. Right. And so I'm going to, well, let me make a couple of observations here. First of all, notice each term has an m in it here, right? And so I can just cancel all of the m's. The mass doesn't matter. That 200 kilograms is not a relevant piece of information, at least as far as answering this question is concerned. The thing I'm after is the v. And so I'm going to move the gh over to the other side, and I'm going to say, look, 1/2 v squared is equal to gh naught minus gh plus 1/2 v naught squared. And if I just simplify this a little bit, I can say, look, all right, I'm just gonna keep going with this. I'm gonna combine these two terms. So I'm gonna say, look, it's g times h naught minus h plus 1/2 v squared. Sorry, v naught squared. Right. All I did was, from this equation, I canceled the m's, I moved the gh to the other side, so I had these two terms, I stuck it in the middle, and then I factored out a g. Notice that what matters is the difference between the two heights. And so I could have picked my initial height as 10, and this one is 40, or this one is 57, and this one is 87. It doesn't matter what heights I pick, as long as they're consistent. The one that's above is the correct amount above the lower one. Because ultimately, when you're calculating potential energy, you're just looking for the difference between them, and they'll subtract out, and so it won't matter. You'll get it one relative to the other. And so usually when I work a problem like this, I find the lowest point in my problem, and I call that one 0. And that way I'm just dealing with positive numbers. We could have picked this one 0, and that would make this one minus 30, because it's got to be 30 less, and it would have worked out just the same. If this was 0 and h was minus 30, it would be 0 minus negative 30, which is 0 plus 30, which is just 30. Instead, we have h naught equals 30, and h is 0, we still get 30 here. Okay. And so now I have this equation. I'm just going to rewrite it here. I have 1/2 v squared equals g times h naught minus h. Get it right. H naught minus h plus 1/2 v naught squared. So I'm going to multiply through by 2, and I get v squared is equal to 2g times h minus h naught plus V naught squared. And that gives me that V is equal to the square root of 2 times 10 meters per second squared times 30 meters plus, so V naught squared is, V naught is 15, V naught squared is 225. That's meters squared per second squared, right? And so that gives me the square root of, so 2 times 10 times 30, 10 times 30 is 300, times 2 is 600, so 825 is 825 meters squared over second squared, which is 28.8 meters per second. And so that's the speed here, 28.8 meters per second. So continuing the roller coaster problem, the roller coaster cart then goes up a ramp angled at 60 degrees. So this is 60 degrees. We'll call that theta equals, right? How high does it rise vertically? Well, once again, I can just look at this from the standpoint of energy, right? It's got V naught, which is 28.8 meters per second. That's what we worked out in the last problem. And then its V at the top is equal to 0 because it's come to a stop. If I want to know how high it went, I go till it stops, right? The distance they're asking for is this, right? That's what they want to know. H equals question mark. I don't know if you can see that on there. But anyway, there it is. And so, so in this problem, I can say, well, look, H naught equals 0. That's the height where it starts. I want to know H final. Once again, I can say the change in potential energy plus the change in kinetic energy equals 0, or PE final plus KE final equals PE initial plus KE initial. And the final kinetic energy is 0 because it stopped. The initial potential energy is 0 because I chose the initial height to be 0. And so all I get is PE final equals KE initial. This is just a conservation of energy statement, once again saying, look, I started out with kinetic energy. At the end, I just get potential energy. And so all of this energy has become this kind of energy, right? And so this just says mgh is equal to 1/2 m v naught squared. Once again, I can cancel the m's, and I get h is equal to v naught squared over 2g, right? And we already know what v naught squared is because we took the square root of it to get 28.8. It was 825. Well, I'll just write it over here, right? The height was equal to v naught squared over 2g, which was 28.8 meters per second squared over 2 times 10 meters per second squared. That was 825 meters squared over second squared divided by 20 meters over second squared. And so 20 is about 41, roughly, 41 a little bit, 41 meters. And so that's how high it went vertically. And if I want to know, if I ask B, you know, if I want to know how far along the ramp this is from the bottom, right? That's 41 meters. If I want to know how far along the ramp this is from the bottom, they're asking me now for the hypotenuse here. Well, sine of theta is equal to opposite over hypotenuse, right? Or the hypotenuse is equal to the opposite side over sine theta, which is 41 meters over the sine of 60 degrees, right? I have to do a quick calculation. About 47 meters, something like that. So that's a little bit about conservation of mechanical energy. Mechanical is kinetic plus potential, and so forth.